So guys, some of you I've talked to about this, the fact that we will not always be doing this crazy like f of x plus h minus f of x over h. We will not be doing that forever. Eventually, we're going to see exactly what the patterns are, and when it's polynomial, we'll know what the derivative is. When it's trig function, we'll know what the derivative is. And some of you, when I've been coming around and kind of checking your answers, you guys have asked me like, oh, is this right? And I'll look at it and say, oh, it should be 1 over 2 root x. I'm like, how did you know that so fast? It's like, well, I will teach you in a couple of days. So don't be too mad at me. Have to teach you the long way first, but we are going to do a couple of examples that will lead us towards what we call the basic derivative rules. And so once we figure out exactly what these patterns are, from this point on, of course on the test I'll still make you do it out the long way a couple times, but from this point on the AP test and everything like that, you'll just be doing these shortened derivative rules. So first one, take the derivative of y equals x squared. So we've actually done maybe not this exact one, but we've done parabolas a couple of times. So we're just going to walk through the process. So remember, step 1 is you take f of x plus h, and so we're going to simplify that up. So that means an x plus h goes in for the x, and then we square it. So please, of course, remember that means we write it out twice and we FOIL it. This is surprisingly where I've seen a lot of mistakes is in the foiling. I see a lot of x squared plus xh plus 2h, or I'm sorry, plus h squared. Make sure that you're writing it out twice and foiling it. If it's not something you can handle in your head, please write it out. Second step is that we take f of x plus h and then subtract f of x. So f of x plus h is this expression that we just had written up above. And then we subtract the original function, which is x squared. This is the step that we've been talking about for the last couple of days, that at the end of this step, you shouldn't have any term that doesn't have a factor of h in it. So this is one term, this is one term. They're both divisible by h, which means they both have a factor of h. So step 3 is to take the expression that I left off with in step 2 and then divide it by h. So this finishes the secant line. So we had, change in y, which is this part right here, and then divided by the change in x. So this finishes off our secant line. So divide everything by h, and this is what we're left with. So remember, what this expression represents is the slope of a secant line from any point x plus h to any point x. So we could plug in any value of x we want. The last thing that we need to do is take the limit as h approaches 0 of the quantity 2x plus h. And of course at this point we've moved past this step and this step. There is no longer an h in the denominator, so we can just plug in h equals 0, and so what we end up with is 2x. So this is the derivative of x squared. Okay, so we got that going for us. That's the first one. We're going to look at the next one, see if we can see some sort of a pattern. So y equals x cubed. Now this one you guys have done out in your notes. You loved it. F of x plus h means we need to take x plus h and we need to cube it. And that does not mean you cube the x and you cube the h. It means that you write everything out 3 times and then you FOIL it. So first of all, we already know what it looks like squared. We have x squared plus 2xh plus h squared. We had that just from the last example, example 1. So this is 2 copies of x plus h, and then we multiply by a 3rd copy of x plus h. So we FOIL this all out. So we've got x squared times x. That gives me an x cubed. And then I have x squared times h. Okay, and then 2xh times x. So that is a 2x squared h, then 2xh times h, so that is a 2xh squared, h squared times x, so that is an h squared x, and then h squared times h gives me an h cubed. So I can combine up some like terms there. Let me see what we end up with. So we've got x cubed. We have these two share the exact same variable part, so I've got 3 of those. And then these two technically share the exact same variable part, so I've got 3 of those. And then my h cubed. Okay, so that's what I get when I FOIL out 3 times x plus h times x plus h times x plus h. Second step is to take my leftovers from step 1 and then subtract the original function, f of x, which is an x cubed. So of course, these cancel out. The end of step 2 comes when every single one of my terms is divisible by h. So you can see I've got 3 terms. They're all divisible by h. So step 3 is to divide out the h. So let's write step 2 divided by h, just a little shorthand there. So divide all of these terms by h. I end up with a 3x squared plus a 3xh and then plus an h squared. So they're all reduced down by a factor of h. So now remember, this represents the slope of the secant line from x to x plus h. My fourth step is to take the limit as h approaches 0. Okay, so again, at this point, we no longer have an h in the denominator or anything like that. So what we can do is just plug in 0, 0, and we're left with just the 3x squared. So that is the derivative of x cubed. Excuse me. So if we're looking at the two of these, we are trying to see if we can figure out some sort of a pattern. So let me put this last one right here. So the derivative of x squared ended up being 2x. The derivative of x cubed ended up being 3x squared. So now normally, of course, now that we're doing this whole flipping the classroom thing, normally you guys would be in class and I would ask you, hey, what do you think the pattern is? And hopefully some of you would figure it out, but I guess I am going to just ruin the surprise for you, tell you the pattern right now. So the way that it works is, see how this is an x squared? My coefficient here ends up being a 2. I've got an x cubed here. My coefficient here ends up being a 3. So the way that this rule works, and some of you might have even figured it out just while you were watching, the old power comes out front as a coefficient, and the power drops down 1. So the 2 comes out front as a coefficient, and then the power of 2 drops down to a power of 1. So that's why I have 2x technically to the first. In this one, the power of 3 comes out as a coefficient of 3. The power of 3 drops down to a power of 2. So that's the pattern, and that's how it's going to work every single time. And I'm sure some of you guys noticed in the homework that we were working on a couple days ago, you had to do an x to the 4th, which meant you had to write it out 4 times, FOIL it out 4 times, and you ended up with 4x to the 3rd. So the power of 4 came out front as a coefficient, and the power dropped down from 4 to 3. So that is what's called our power rule. So anytime you have a power function, x raised to a power, now we're going to do some notation here. Rule 1 that we already talked about was the derivative of a constant function. Say like a 2x minus 4, the derivative is just 2. Or like negative 7x plus 1, the derivative is just negative 7. Derivative, remember, is another word for slope. And we've known that the slope of a linear function is just the m in the equation. We've known that since Algebra 1. So that was Rule 1. Rule 2 is the power rule. So remember some of our notation that we've seen. And I'll review it with you guys real quick. So we've got d over dx, and then in the brackets we have our function. So we read this as d by dx. The d stands for derivative, and then down here in the denominator, the variable tells us what we're taking the derivative with respect to. And I know that's kind of a weird thing, but with respect to x, for now, just means that the variable here is an x. Eventually, if you guys move on to Calc 2, Calc 3, you could be taking the derivative with respect to a different variable. Let's not even talk about that yet. So again, this is read as d by dx, which means the derivative with respect to x of our function x to the n. So if we're trying to take the derivative of x to the n, the pattern we were just saying was the n comes out front times x, and then the old power drops down 1. So that's where we got the 3x squared or the 4x cubed. So even if you wanted to take the derivative like x to the 100th, I'm sure you can imagine how absolutely god-awful that would be to do something like that by hand. The derivative is just 100 times x to the 99th. You can do that with any whole number power, even any fraction power works as well, any power at all. The constant multiple rule, this is something that we kind of saw with limits a little bit, and this is if you've got a constant multiplied by a function. So say your function is like a power, for example, like x cubed or something like that, and then c is just a constant. So what our rule says is that the constant, it's not really going to play into the derivative, so we can just pull it out front. So then it would be c times the derivative of f of x. So now remember again, f of x could be any function that we're talking about, but this says that the constant can just move out front and we'll multiply it in later. So then it's going to be the constant times, now we're just going to write down a different notation, the derivative of f of x, we write as f prime of x. So rule 3 is we've got this constant multiple rule. All the constant multiple rule says is that you can move the constant out front, take the derivative of the function, and then you just multiply in the constant when you're done. So I'm sure you guys saw examples like that with like 2x squared or 3x squared or something like that. All right, the sum and difference rule, this is to help us do entire polynomials. If you're taking the derivative of the sum or the difference of two different functions, like this. So if you're taking the derivative of, say, an entire polynomial or some sort of phrase, some sort of algebra expression, you can just split it up and you take the derivative of the first piece and then plus or minus, whatever you've got in the problem, the derivative of the second piece. So in our shorthand again, remember the derivative of f of x, we just write that as f prime of x. And then plus or minus the derivative of g of x is just g prime of x. So whenever you've got a sum or difference, and that doesn't just have to be 2 terms, it can be like 8 terms in a row, you just take the derivative of each one of them separately. All right, so example 3, we are going to apply these 4 rules that we've done so far. So we've got this crazy function, so our function p, this dp by dt, that means the derivative of p with respect to t. And so this is our function p. The variable that we're using as our independent variable is t, so that's all this notation means. Now, keep in mind, if we had done this the way that we've been doing it for the last couple of days, that seems absolutely terrible. We've got 4 pieces, a 4-piece polynomial. You'd have to plug in an x plus h, or I guess a t plus h, in every single one of those. But now we've got all of these rules. So the first thing that we do, you're kind of applying this sum and difference rule. So to take the derivative of this entire expression means to just take the derivative of each individual piece and just add them together. So we are going to write dp by dt equals, or you could write p prime. That would be another way to write it, just so you know. You could also write p prime. But dp by dt is just the notation that we use, so we might as well keep it. So we start with each piece. The derivative of t to the third. So this falls under the category of power rule. So t to the third, the 3 comes out front as a coefficient, and then the old power drops down 1. So the derivative of t to the third is 3t to the second. Okay, and then plus. So this is the way the sum and difference rule works, is then you just add all the different pieces together. So then plus whatever the derivative of 6t squared is. So first thing I need to do is I follow my constant multiple rule. So the 6 just comes out front. And then I multiply by the derivative of t squared, which the derivative of t squared, the 2 comes out front. So 2 times t, and then my power drops down to a 1, technically. And then minus again, I'm still using this sum and difference rule with every part. Then the derivative of 5/3 t. This piece is actually linear. So that goes with rule number 1. The derivative of, or I guess kind of it goes with the power rule. So you could say that the 1 comes out front and the power drops down to 0. But this is a linear piece. The derivative of a linear function is just m. So if we plotted just this function, we know the derivative would be a negative 5/3 because this would just be a linear function. So negative 5/3 would be the slope. And then plus the derivative of a constant function, because 16 would just be a horizontal line. The derivative of a horizontal line is just 0. So the derivative of a constant will always be 0. So that's a little bit messy. Let's clean this up. So we've got 3t squared plus, this ends up being a 12t when I multiply that together, and then minus 5/3. So this is your final answer. This is the derivative of your function p that we started off with. And again, what this tells you is what the slope to this curve is at any given value of t, any value that you would want to plug in at all. So if you want to know the derivative at 1, you would plug 1 into this function. If you wanted to know the derivative at -4, you would plug -4 into this function. And that just represents the slope on this line at any given point that you could ever want. So it's a little bit more useful to find an entire function, like we've been doing for the last couple days, rather than finding the derivative just at one point, which is what we did the first day or two. All right, example 4. This one's kind of a more interpretation question. It asks if this curve has any horizontal tangents. So we've been talking about what horizontal tangents mean. Anytime that you see this phrase, horizontal tangents, that means the tangent line is a horizontal line. Remember, horizontal lines have a slope of 0, and so we're trying to find out if there's any point where the derivative is 0. So you could write y prime, you could write dy by dx, many, many different notations that you could use there. So that is what we're looking for. We want the derivative to be 0, which means first we need to find the derivative. So we'll start with our function right here, and we're going to use the same exact rules that we just talked about up above. So for now, like from this point on in the chapter, gone are the days where we're actually doing the derivative out by hand with the x plus h and the x and everything like that. So we're just going piece by piece, kind of using the sum and difference rule. So the derivative of x to the 4th, this is the power rule. So the 4 comes out front as the coefficient, and the power drops down from 4 to 3. Next one, minus, and there's a 2 out front, so I'm going to do a power rule here, and then times the derivative of x squared. So the derivative of x squared, the 2 comes out front as a coefficient, my power drops down to 1, and then plus the derivative of 2 is just 0. Okay, so again, clean that up a little bit. Got 4x cubed and then minus 4x, and there's no need to write the plus 0. So that represents our derivative at any given point. We're trying to figure out if there's ever a point where the derivative is equal to 0. So let's take our derivative formula and set it equal to 0. So this is all just algebra from this point. We're taking this expression right here. You're going to factor it down, solve for x. So I can factor out a 4x, and then in parentheses I have an x squared minus 1 equals 0. So when I set each piece equal to 0, when I set the 4x equal to 0, I come up with x equals 0. And then when I set the x squared minus 1 equal to 0, I could factor that down using the difference of squares. And so I'd come up with positive or negative 1. So just to show you guys, just so you can get kind of a visual on this, I'll show you what this graph looks like. So we're going to graph the function x to the 4th minus 2x squared plus 2. So I'm a big visual person. I know a lot of you guys are probably visual people. I'm always going to show you exactly what something looks like, especially when we're talking about tangent lines. So if we graph this function, what we came up with said that the curve has horizontal tangent lines at 0, at positive 1, and at negative 1. And if you look right here, that's at 0, comes to a high point, so it's increasing, then it stops for a second, and then it starts decreasing. So positive slope, slope of 0, negative slope, and then we've got the exact same thing happening at these 2 points, at positive 1 and at negative 1. So just for a second, I'm going to zoom in kind of right around this piece right here so we can get a better view on it. It's a little better. So again, right here, and then at positive 1 and negative 1, we've got these slopes of 0. That's where the graph switches from positive to negative slope. Because if, say here, like it's decreasing, that means we've got a negative slope. Right in here, it switches from decreasing to increasing, so the slope must have been 0, even just for an instant. And then same thing here. I have a positive slope, then a negative slope, so it must have been 0 right here. Then I have a negative slope, then a positive slope, so it must have been 0 right here. So I've got 3 spots where I would have a horizontal tangent line to my graph. All right. Next one. All right, so we're going to look at this window that's given in this graph right here, horizontal tangents. So here is what we're going to look at. So I'm going to swap out this graph. So I would love it if you guys could follow along with me, just because I want you to be able to know what you're doing on your calculator. So plot this graph. So 0.2 x to the 4th minus 0.7 x to the 3rd minus 2x squared plus 5x plus 4. Okay, and they want us to look in a specific window, because clearly this is kind of taking up the whole space here. So if you're on an Inspire, hit Menu, Window Zoom, and then hit Window Settings, and you can change. So we want negative 10 to 10. You just hit Tab in between every value, and then negative 10 to 10. So this is the specific window that I asked you guys to look in. If you have an 84, there's a window button, like right up along the top here, and you just hit the window button and change it from negative 10 to 10, and then negative 10 to 10. So here's what we're looking at. We've got 3 horizontal tangents. So first of all, we want to take a look at our derivative. And so if we're looking at this graph right here, we're trying to identify this point, and this point. So we've got 3 horizontal tangents. So let's come up with the derivative. So y prime equals, so looking at this function right here, we're going to try to find the derivative first. So one of the things you may have noticed, like look at this one for example. I pulled the 2 out, but then my power of 2 came out front here. What ended up happening is these two multiplied by each other and I got 4. So you can kind of absorb the constant multiple rule and the power rule into one. What ends up happening is this 2 comes out front, it multiplied by the 2 that was already there, and that's why my constant is 4. Same thing here. My 2 came out front and it multiplied by the 6 that was already there. That's where the 12 came from. So I can do the same rule right here. Like the 4 comes out front, multiplies by the 0.2 that was already there. So I have 0.8, and then my power drops down to 3. Then here the 3 comes out, multiplies by the 0.7, so minus 2.1x. Then my power drops down to a 2. Here this one's nice and easy, whole numbers. 2 comes out, multiplies by the 2 that was already there. I get 4x to the first, technically. Now 5, you could consider yourself to be doing a power rule. Say there's a power of 1. The 1 comes out front, multiplies by a 5. That's where the 5 comes from. And the power drops down to 0. So x to the 0 is just 1. So you could consider yourself to be doing the power rule, or you could consider yourself to be doing the linear rule, where the derivative of m times x is just m. And then plus the derivative of 4, of course, is 0. So I'm just going to leave that off. So here's my derivative. What we are looking for on the graph is where the derivative is equal to 0, because that's our horizontal tangent line. So now, of course, this is very messy in terms of actually trying to factor it. So I'm going to look on the same graph. Hit tab if you've got an Inspire, or just add in another graph into your y equals if you've got an 84. So add in this derivative. So while they're on the same graph, I want to point out a couple of things to you. So I've got these two crazy functions that if we look closely at them, this one right here, so the red one, I don't know if you can see that they actually are different. This red one is the one that goes like this. Okay, whoops, I should not have drawn on there. Now it looks even more confusing. So the red one starts up here at the top. This one's the quartic, kind of looks like a big W. And then the black one, this is cubic. So I'm going to get my derivative graph so that it's kind of highlighted. There we go. That should hopefully help. So what we're looking at, see how right here we had a high point, and so we said that there would be a horizontal tangent line there. Well, if you look directly below, that's exactly where the derivative crossed 0. And then same thing right here. I've got a low point, so we said the derivative would be 0. And if you look above, that's exactly where my derivative graph hit 0, hit the x-axis. And one more point, that's where my original graph had a low point. We said there'd be a horizontal tangent there. And if you trace up, that is exactly where my derivative hit the x-axis. All right, so we are trying to find, if we clear out, I want you to clear out the original one, because otherwise it's going to be harder to find our zeros. So whichever graph you're looking on, or whichever type of calculator, that you're looking at, please just delete out the first one because it's going to be a lot easier to find the zeros. So if you're on an Inspire, hit Menu, and then Analyze Graph, and then we're going to find the zeros. So number 1. So for lower bound and upper bound, we've done this a couple times in class. You just literally are moving your touchpad back and forth. So the lower bound, we click below it, and then just move over until we catch one of them. So there is negative 1.86. That's one of them. And then we can do the same thing again. Menu, Analyze Graph, 0. And then we can click right here, move over here, and that is a 0.948. That's another one. And do this one more time. Menu, Analyze Graph, 0. And same thing. Click to the left, arrow your way over here to the right, and we get a third one of 3.54. So our zeros, these occur at x equals, we had negative 1.86, 0.948, and 3.54. Okay, so now let me show you really quickly on the 84. So on the 84, we've got the derivative graph plugged in here. So 0.8x cubed minus 2.1x squared minus 4x plus 5. Okay, so graph that. We want to be in that specific window. So graph it, and then you should be looking at, the exact same graph that we saw when we were looking on the Inspire. So here, to find your zeros, you hit second and then trace, where it says calc up above it, and you get the exact same menu that we just saw on the Inspire. So select 0. Now here you can kind of type in your own left bound and right bound. So if you're looking at this one, you're like, oh, well, it looks like it's definitely between -3 and -1. So for the left bound, you can type in -3 and hit enter, and then type in -1 and hit enter, and then I have no idea what guess means. Just hit enter again. Now this is nice because it gives us more digits, and I'll show you guys how to get more digits on the Inspire as well. So that's the first one, and then just do the exact same thing again. So second calc, 0. The next one looks like it's probably between 0 and 1. So hit 0, enter, 1, enter, enter one more time for whatever that means. We get the second one, and one more time, second calc, 0. This one looks like it's in between 3 and 4. So 3, enter, 4, enter, enter one more time for whatever that means, and there is your third 0. All right, so we've got the same 3 values in the 2 different calculators, just to show you both of them there. All right, best derivative ever. A little bit less of a lead up when you guys are actually not in class with me. So the derivative of e to the x. Okay, so we did all the polynomial ones. We are moving now into our first, we've got this exponential function here. So fun fact, the derivative of e to the x is e to the x. It is its own derivative. It's a very fun, very exciting little derivative here. Now, for the proof of the best derivative ever, just to show you guys, I'll just show you guys real quick. So remember, you're taking the limit as h approaches 0. You plug in x plus h into the function, and then minus, you plug x into the function, and then all of that over h. So the first thing that we can do in the numerator, we can factor out an e to the x. So remember, you should have your limit clause. So factor out an e to the x, and that leaves us with an e to the h minus 1, and then that is over h. Remember, these two, if we divide these up, when we multiply these two things back together, we'd add the powers. So since the powers were added over here, this is a perfectly legitimate step to make. And then here, this part's a little bit tricky. Since the variable I'm using is h, I can actually pull the e to the x right out, since that has nothing to do with h. And then I'm looking for this limit here. So what I'm going to do is show you what that becomes in the calculator. So we are going to plug in e to the x minus 1 and then divided by x, because of course we can only use x, we can't use h. And then let's just look at a table. Let's see what happens as x approaches 0. So 0.1, 0.01, 0.001. So you can see these values are getting very, very close to 1. All right, so that limit ends up being 1. So this is e to the x times what turns out to be 1, and so that derivative is in fact e to the x. All right, so we'll be using that in later sections, but I just wanted to show you that now. We've got 2 more quick examples here where we're just using these basic derivative rules. So this one, p of z. This one seems a little tricky. So like, well, I've got 2 things multiplied together. I don't have a rule for products yet. Well, what you can do is just FOIL and simplify it up. So p of z, if we FOIL this out, we've got 3z times 2z, which is 6z squared. And then outside, inside, I get 3z minus 2z, which is just a z. And then negative 1 times positive 1 gives me a negative 1. So that is the equivalent of p of z, so I just leave it exactly like that. So I want p prime of 2. So if we're going to find the derivative at a certain value, you've got to find the derivative, the original derivative function first. So I'm going to find p prime of z. So taking the derivative of each piece, remember the power rule here, the 2 comes out front, multiplies by the 6 that was already there, and I get 12. My power pops down to just z to the first. And then plus the derivative of just a 1z is just 1, because that piece is linear. And then the derivative of negative 1 is 0, so I'm not even going to write that. Then I want to find p prime of 2, so all I do is I plug 2 right into that derivative function. Okay, so it simplifies up to be 25. Okay, so one more, very similar to what we had going on up here. We didn't have a rule yet for products. We will tomorrow. And here we don't have a derivative rule for quotients either, but we can very easily just split these two up. So take the root x and divide it by x, and what I get is 1 over the square root of x. So I'm going to write this out first. And then plus, put the 1 over x. So I want to write these as powers because I have a rule for powers. So root x, remember, is x to the 1/2, and then over x, which is x to the first. So that ends up being x to the negative 1/2 if you simplify those powers down. And then plus 1 over x we know is x to the negative first. So these two things are exactly equivalent. I'm just writing them as powers so that I can use my power rule. Okay, so take the derivative. So I'm sorry, this is still just f. That is not f prime yet. Now I'm going to start taking f prime. So what I do is I take my power, put it out front as a coefficient, so negative 1/2, and then my old power, we subtract 1. So negative 1/2 minus 1 gives me a power of negative 3/2. Now you guys actually found this derivative the long way a couple days ago. And then plus x to the negative first, the negative 1 comes out front as a coefficient. My power, we subtract 1, so negative 1 minus 1 gives me negative 2. So that's my derivative. Let me write it in a slightly prettier way. Negative 1 over 2x to the 3/2, and then minus 1 over x squared. So that is my derivative. Now what I want is the tangent line at x equals 16. So I want f prime of 16. Okay, so I plug that in. So I've got negative 1 over 2 times 16 to the 3/2, and then minus 1 over 16 squared. All right, so when I plug this in, I'm just going to go right into the calculator. Let's go Inspire. It's a little clearer. Okay, so negative 1 over 2 times 16 raised to the 3/2 power, and then minus another fraction, 1 over 16 squared. Okay, so my calculator automatically gives me a decimal. It is in fact negative 3 over 256, which we could figure out if we simplify that up by hand. Or if you wanted a decimal, that is that. I would not write that decimal. I would write the fraction. So I'm just giving you a little shortcut here. This ends up being negative 3 over 256. Nice, neat value. Now remember, for the tangent line, we also need the y value. So we're going to plug 16 into the original function. That gives us the y value. So the original function, we have root 16 plus 1, and then over 16. So root 16 plus 1 is 5, and then over 16. So we plug it into point slope form. We've got y minus the y value, which we just found was 5 over 16, equals the value of the slope, and then in parentheses, x minus the x value. So remember, you just leave it exactly like that. All right, that's it.